Oh, hi there, and welcome to Learning in These Astronomical Streets. My name is Chris, and in this video, we are going to read the article What is Dark Matter, written by Nolan Taylor Tillman, and with contributions by Teresa Poltarova. And it was last updated on August 6, 2024, not long ago. And again, I'm still doing my research into the building blocks of the universe. I've done the what is dark energy, so we're going next up with what is dark matter. Not going to make this intro too long. Let's check it out. Transition. So, what is dark matter? Dark matter is the mysterious stuff that fills the universe, but no one has ever seen. So, dark matter constitutes over 80% of all matter in the universe, yet it remains unseen by scientists. Its existence is inferred because without it, the behavior of stars, planets, and galaxies will be inexplicable. Here's what we know about it, or rather, what we think we know about it. Dark matter is entirely invisible, emitting no light or energy, making it undetectable by conventional sensors and detectors. Scientists believe that the key to its elusive nature lies in its composition. Visible matter, also known baryonic matter, consists of baryons, an overarching name for subatomic particles such as protons, neutrons, and electrons. Scientists only speculate what dark matter is made of. It could be composed of baryons, but it could also be non-baryonic, which means consisting of different types of particles. Most scientists think that dark matter consists of non-baryonic matter. The leading candidates are WIMPs, weakly interacting massive particles, which are thought to be 10 to 100 times the mass of a proton. However, their weak interaction with normal matter makes them challenging to detect. Among these, neutralinos, hypothetical particles that are heavier and slower than neutrinos, are the top candidates, though they are not yet being observed. So, I, as far as I can understand so far, is that the particles dark matter is composed of are theoretical particles that they just come up with to explain what dark matter is because they don't really have an idea. It doesn't contain protons, neutrons, or electrons. So it's like, okay, so if there is dark matter, there should be a particle, but maybe it's a particle that we don't know what it is. I think that's why CERN with the Hadron Collider, they're trying to detect to see if they can discover new type of particles. But I digress. Transition. Sterile neutrinos are another candidate. Neutrinos are particles that don't make up regular matter. A river of neutrinos streams from the sun, but because they rarely interact with normal matter, they pass through Earth and its inhabitants. That means neutrinos could be like all over the place. There are three known types of neutrinos. A fourth, the sterile neutrino, is proposed as a dark matter candidate. The sterile neutrino would only interact with regular matter through gravity. One of the outstanding questions is whether there is a pattern to the fractions that go into each neutrino species. TAS D. Young, an associate professor of physics and astronomy at Michigan State University and collaborator on the IceCube Neutrino Observatory in Antarctica, told Space.com. An IceCube neutrino. I have so many jokes about this. It's part of the NWA. Is it F the police? I digress. The small neutral action and the uncharged photons, both theoretical particles, again, they're just making up particles to explain this dark matter, are also potential placeholder for dark matter. There is also such a thing as antimatter, which is not the same as dark matter. Antimatter consists of particles that are essentially the same as visible matter, particles but with opposite electrical charges. These particles are called antiprotons and positrons, or accept anti-electrons. Man, they're trying to become very creative with these names. When antiparticles meet particles, an explosion ensues that leads to the two types of matter canceling each other out. Because we live in a universe made of matter, it is obvious that there is not that much antimatter around. Otherwise, there will be nothing left. Unlike dark matter, physicists can actually manufacture antimatter in their laboratory. What? Interesting. Transition. You know what I think I've mentioned this quickly. I work in the field, in the IT field, and what I feel is that these scientists have all these type of names and placeholders to actually explain dark matter. They just, and they're theoretical particles that they just kind of make up. To me, in programming terms, and I think somewhat in mathematical terms, they usually put these placeholders like as variable to say like, okay, if we're going to calculate this, we need to give a name to a as a placeholder for to pretty much explain certain things. So to say, okay, we are going to call something antimatter. Antimatter is a hypothetical term to, sorry, photons or neutral action or uncharged photons. We're going to use this as placeholders to be able for us to calculate whatever we need to calculate to explain the expansion of the universe, or not the expansion of the universe, my bad, but to explain the matter, the dark matter, pretty much. So that's pretty much how I understand it so far. So transition. Does dark matter exist? I wish I knew. What we do know is that if we look at physical galaxy, take account of all the matter that we see, stars, gas, dust, and use Newton's law of gravity and motion, or more correctly, Einstein's general relativity, to try to describe the motions of that material. Then we get the wrong answer. The objects in galaxy, nearly all of them are moving too fast. There should not be enough gravity to keep them from flying out of the galaxy that they're in. The same thing is true about galaxies moving around in clusters. And there are two possible explanations. One, there is more stuff, matter, that we don't see with our telescopes. We call this dark matter. And two, Newton's law and even the general relativity are wrong on the scale of galaxies and everything bigger. This idea is usually called modified gravity because we need to modify general relativity or modify Newtonian dynamics, MOND. You know, I'm not mad at that. Especially at the point of general relativity. One of the things about general relativity is that it's relative to the observer. Let me transition to put out my idea. The universe is so big that this calculation of Einstein are very understandable, yes, but at our scale, at our level, at our understanding and our limitations are human. But and the reason why this part, the second explanation in this particular article, for me, what it makes sense is that Einstein's general relativity doesn't fit well with quantum mechanics and quantum physics. So there's a limitation at a quantum level, at a very, very small level. So it should be true that, and I will include Newton as well, both Newton's law and general relativity by Einstein should also have a limitation when we go to an astronomical level. I think that their physics are right and they're understandable and they make absolute sense at a level that we humans can perceive physics. But we humans have a limitation. We can't go, we have nothing that we can accelerate at the speed of light. I think the CERN, the Super Hadron Collider, they're trying to move small particles at the speed of light, and they just reach it. They can't even reach it. They're close to it, but they can't reach it. And this is where things start to get a little spooky and things that don't make sense. This is where we go to a different realm. So To me, the way I can describe it is like we have two different realms. This is just my personal hypothesis. Is that we have three physical realms. There is the astronomical realm that we can't reach. The normal, regular physical realm, that's the physics that of the universe that we know of and that we're comfortable of. When we talk about the different type of theories and discoveries that have been made by our amazing physicists throughout human history, and the quantum realm of physics. And those two realms, the astronomical realm and quantum realms, are two realms that we can't touch. We can't get there. You see, we need to be at a, and this is where I'm going to put my tin hat, we need to be at a different dimension to be able to observe this realm and actually calculate and come up with actual, let's just say, to understand something like dark matter and dark energy. That's pretty much what it is. And even gravity we know more, a little bit more, because yes, even though gravity is something that we don't quite understand, but we can understand it a little bit in our realm, the realm that I'm talking about, the human physical realm. But if we're in a different dimension, a higher dimension plane, maybe we'll be able to understand it even better. So that was my little hypothesis. So let's continue. So mostly cosmologists believe that the answer is that the behavior of galaxies is explained by dark matter. Why? Partly because it has been very hard to write down successfully theory of MOND, which is modifying Newtonian dynamics, or modified gravity. And partly because it turned out that when we turn our microwave telescopes to look at cosmic background radiation, or CMB, the light from the early universe, it turned out that according to GR, general relativity, the same amount and type of dark matter was also required to explain the behavior of the sound wave that traveled in the universe when it was less than 500,000 years old. Wow. And whose imprints we are able to see? Modified gravity struggles to provide a unified explanation across all these systems, galaxies, clusters of galaxies, the universe, but we don't yet know what dark matter is made of. Does dark matter have mass? If dark matter exists, it must have mass. Massless dark matter would not behave in ways that solve the problems that dark matter addresses. What does dark matter do? The two things we know for sure about dark matter, assuming it exists, is that it exerts gravity, has mass, and that it moves slowly compared to the speed of light. How do you look for dark matter? Since we don't know what dark matter is, the answer is, for every possible candidate for the dark matter, there is a different strategy to search for it. People build giant detectors deep underground to get away from all the other particles streaming through the environment around us, and look for signals of the dark matter hitting their detector after passing through the earth overhead. I happen to be looking for a form of dark matter that is quite massive, between about 100 grams and many tons, and will have more easily visible effects. But because it is massive, it is very rare. We know how much total mass of dark matter there should be. So, if the individual dark matter particles are heavy, there are fewer of them. For example, if it hit a rock, it would melt the rock along its path as it zoomed through the rock. We can look for the scars of those passages, for example, in granite countertops. Oh. But if we cannot see dark matter, how do we know it exists? The answer is gravity. The force exerted by objects made of matter that is proportional to their mass. The force exerted by objects made of matter that is proportional to their mass. Since the 1920s, astronomers have hypothesized that the universe must contain more matter than we can see, because the gravitational forces that seems to be at play in the universe simply appear stronger than the visible matter alone will account for. But another hypothesis came up to mind. So imagine there is no dark energy in dark matter, and we understand that gravity is responsible to pretty much glue together all particles that we know of. And that's how stars, planets, galaxies form. So, in the absence of dark matter and dark energy, would all of these stars and planets and galaxy all bunch up together and have a singular body in the universe? That's very interesting to think about. I have to reflect on that. That just came up to me right now. Anyways, transition back. Motions of the stars tell you how much matter. Motions of the stars tell you how much matter there is. Peter Van Dokkum, a researcher at Yale University, said in a statement, quote, "They don't care what form the matter is, they just tell you that it's there." Astronomers examining spiral galaxies in the 1970s expected to see material in the center moving faster than at the outer edges. Instead, they found the stars in both locations travel at the same velocity, indicating the galaxies contained more mass than could be seen. Studies of gas within elliptical galaxies also indicated a need for more mass than found in visible objects. Clusters of galaxies will fly apart if the only mass they contain was the mass visible to conventional astronomical measurements. Different galaxies seem to contain different amount of dark matter. In 2016, a team led by Van Dokkum found a galaxy called Dragonfly 44, which seems to be composed of almost entirely of dark matter. On the other hand, since 2018, astronomers have found several galaxies that seem to lack dark matter altogether. The force of gravity doesn't only affect the orbits of stars in galaxies, but also the trajectory of light. Famous physicist Albert Einstein showed in the early 20th century that massive objects in the universe bend and distort light due to the force of their gravity. The phenomenon is called gravitational lensing. By studying how light is distorted by galaxy clusters, astronomers have been able to create a map of dark matter in the universe. The vast majority of astronomical community today accepts that dark matter exists. Quote, "Several astronomical measurements have corroborated the existence of dark matter, leading to a worldwide effect to observe directly dark matter particles interaction with ordinary matter in extremely sensitive detectors, which would confirm its existence and shed light on its properties." The Gran Sasso National Laboratory in Italy, LNGS, said in a statement, "However, these interactions are so feeble that they have escaped direct detection up to this point, forcing scientists to build detectors that are more and more sensitive." Despite all the evidence pointing towards the existence of dark matter, there is also the possibility that no such thing exists after all, and that the laws of gravity describing the motion of objects within the solar system require revision. Dark matter appears to be spread across the cosmos in a net-like pattern. Picture is interesting. A mysterious glow coming from the center of the Milky Way might be caused by annihilating dark matter. Interesting. Dark matter appears to be spread across the cosmos in a net-like pattern, with galaxy clusters forming at the nodes where fibers intersect. By verifying that gravity acts the same both inside and outside our solar system, researchers provide additional evidence for the existence of dark matter. Things are even more complicated as in addition to dark matter, there also appears to be dark energy, an invisible force responsible for the expansion of the universe that acts against gravity. I did made a video about that, go check it out. But where does dark matter come from? The obvious answer is that we don't know. But there are a few theories. A study published in December 2021 in the Astrophysical Journal argues that dark matter might be concentrated in black holes, the powerful gates to nothing that due to the extreme force of their gravity devour everything in their vicinity. As such, dark matter would have been created in the Big Bang together with all other consulting elements of the universe as we see today. Stellar remnants such as white dwarfs and neutron stars are also thought to contain high amount of dark matter, and so are the so-called brown dwarfs, failed stars that didn't accumulate enough material to kickstart nuclear fusion in their core. This article is long. Since we can't see dark matter, how can we study it? There are two main approaches. Astronomers analyze its distribution by observing material clustering and object motions in the universe. Meanwhile, particles physicists aim to detect the fundamental particles that compose dark matter. An experiment mounted on the International Space Station called the Alpha Magnetic Spectrometer (IMS) detects antimatter in cosmic rays since 2011, it has been hit by more than 100 billion cosmic rays, providing fascinating insights into the composition of particles traversing the universe. Quote, "We have measured an excess of positrons, the antimatter counterpart to an electron, and this excess can come from dark matter." Samuel Ting, AMS lead scientist and a Nobel laureate with the Massachusetts Institute of Technology, told Space.com. But at this moment, we still need more data to make sure it is from dark matter and not from some strange astrophysics source that will require us to run a few more years. Back on Earth beneath a mountain in Italy, the LNGS Xenon 1T is hunting for signs of interaction after WIMPs collide with xenon atoms. Quote, "A new phase in the race to detect dark matter with ultra-low background massive detectors on Earth has just begun with Xenon 1T. Project spokesperson Elena April, a professor at Columbia University, said in a statement, quote, "We are proud to be at the forefront of the race with this amazing detector, the first of its kind," end close quote. The large underground xenon dark matter experiment LUX, seated in a gold mine in South Dakota, has also been hunting for signs of WIMP and xenon interactions, but so far the instrument has revealed the mysterious matter. Though a positive signal would have been welcome, nature was not so kind. Cham Gag, a physicist at University College London and collaborator on LUX, said in a statement, quote, "Nonetheless, a null result is significant as it changes the landscape of the field by constraining models for what dark matter could be beyond anything that existed previously." The Ice Cube Neutrino Observatory, an experiment buried under the frozen surface of Antarctica, is hunting for the hypothetical sterile neutrinos. Sterile neutrinos only interact with regular matter through gravity, making it a strong candidate for dark matter. Experiments aiming to detect elusive dark matter particles are also conducted in the Powerful Particles Collider at the European Organization for Nuclear Research, CERN, in Switzerland. Several telescopes orbiting Earth are hunting for the effects of dark matter. The European Space Agency's Planck spacecraft, retired in 2013, spent 4 years in the Lagrangian point 2, a point in the orbit around the Sun where a spacecraft maintains a stable position with respect to the Earth. I think it's close to where the James Webb Space Telescope is, or is that Lagrangian point 1? Or in one of those points. Mapping the distribution of the cosmic microwave background, a relic from the Big Bang in the universe. Irregularities in the distribution of this microwave background reveal clues about the distribution of dark matter. In 2014, NASA's Fermi Gamma Ray Space Telescope made maps of the heart of our galaxy, the Milky Way, in a gamma ray light, revealing an excess of gamma ray emission extending from its core. Quote, "The signal we found cannot be explained by currently proposed alternative, and is in close agreement with the prediction of very simple dark matter models," lead author Dan Hopper, an astrophysicist at Fermilab in Illinois, told Space.com. "The excess can be explained by annihilation of dark matter particles with a mass between 31 and 40 billion electron volts," researchers said. "The result by itself isn't enough to be considered a smoking gun for dark matter. Additional data from other observing projects or direct detection experiments will be required to validate the interpretation." James Webb Space Telescope, launched after 30 years of development on December 25th, 2021, is also expected to contribute to the hunt for the elusive substance. With its infrared eyes able to see to the beginning of the time, the telescope of the century won't be able to see dark matter directly, but through observing the evolution of galaxies since the earliest stages of the universe, it is expected to provide insight that have not been possible before. The European Space Agency Euclid mission, launched on July 1st, 2023, is currently on the hunt for dark matter energy. The mission aims to map the geometry of matter in the universe, specifically the distribution of galaxies, to learn more about the elusive dark matter. This is a long article, but it's very good though. Very, it has a good content. Nola Taylor Tillman was the contributing writer, so it's great. I think out of all the articles I've read so far in regards to gravity, dark energy, and this one about dark matter is the best one so far. I don't want to take nothing about the articles that I've read from the NASA's website, but I feel that the writers of NASA website could actually do with a writer like Nola Taylor Tillman. And who was the contributor? There was a contributor also. And Teresa Poltarova, to give thorough information and articles in regards to their topics. Anyways, see the video is going very long. Thank you very much for watching. If you're still here, remember to drink water, and I'll see you on the next one. Take care.